You will see that you design a linear set of linear bearings for a system. How are you going to support the load, and how will it move throughout its travel? Is it intrusive into the area, or is it non-intrusive? And then separate from that is what kind of drive mechanism are you going to use to move it back and forth? This is where you get into the, this leads directly into motor sizing, actually. And as you look at motor sizing, you will see that there's rotary loads, like there's, essentially the first one would be direct drive rotary. First category is rotary motion versus linear motion. We spend a lot of time on linear motion. Most motors start with rotary motion, and to get linear motion, there has to be some translation. The only exception is if you use a linear motor, and they make both linear steppers and linear servos, and I showed you the example of the linear stepper a little bit earlier. There are direct drive motors that are much larger. Essentially, they look, I'll kind of draw it. They, instead of hot dog style motors, which is what you have, and the hot dog style motor is the rotor looks something like this, and it is long and skinny. And the idea here is, if I turn this on its side, that you have a small radius. This is R, and F is here at the air gap in a regular motor. This is the shaft right here. This is the right here. This is the outer edge of the magnetics. That's the air gap. So let me air gap. I'm bringing up the direct drive, the motors first before we actually get into mechanics, because I don't want to forget to mention them, because they're becoming so much more important as more and more axes of automation get used in the world, and they try and do more and more accurate positioning. The only way to do that is to get rid of efficiencies, get rid of frictions, get rid of translation methods, which means make the motor start out going in the right direction that you want to go in the first place. Well, we were doing R cross F, but the R cross F is a very small R, and then you get longer and longer motors to try and get more torque. The torque, R cross F on the hot dog. And by hot dog, I just mean long and skinny, meaning that the rotor, the R and the F, that R is small. And so in order to get more torque, you ask the rotor to get longer and longer until you get longer and longer motors. And you saw that when you were doing stepper motors, you could get single stack, double stack, triple stack motors. And all it did was multiply the torque, but it kept the diameter the same. So R stayed the same, and you increased F to get more torque. The other way to get more torque is to use a direct drive. And I'll draw it for you. Examples of this, people who make these are, lots of motor manufacturers make these now, but one of the best ones that I've used is the Kollmorgen. You'll notice that I like Kollmorgen motors a lot. I use them anytime I go brushless motors. I've been through enough motor factories and seen motor manufacturers make motors that I pretty much like. They come out of Virginia. They're made in the United States, which I like, and they make awesome motors. So Kollmorgen makes them. The key to how they look, though, is they look more like this. So this would be anywhere from, a small one might be 4 inches to a large one might be 12 inches in diameter. And they could be anywhere from, 1 to 10 inches in length. But the key to these is that instead of having a shaft that like this one had a motor shaft that came out each side, and that was the rotor of your stepper motor. The key to this is that here is actually a fairly large hole, and around the edges of this are mounting holes. So what they've done in this, you still have to have a bearing to make it spin, but instead of little, like on this, instead of a little round bearing here on this end and another one on this end that are fairly just standard round bearings, rotary bearings that it spins on. This one, the bearing inside of here is actually fairly large diameter of a bearing here, and it's a fairly large diameter bearing down in here. And this, so the air gap would be something like out here is where you would have the air gap between the stator, meaning the part that stays in one place, and the rotor. So this part out here, the part that stays, that's how I remember it, is called the stator. And then the part inside is the rotor. And guess why it's called the rotor? Sometimes they call it the armature. I don't care. I like to call it the rotor because it rotates. So it makes it pretty easy. But R cross F on this, it has a huge F and it has a huge R. And the key is it actually has, in order to get that large diameter, you have to put in, this is a pretty expensive bearing, but it also can support load. Now, one of the things that when you're looking at stationary. All right, stays in one place, whatever. So one of the things that when you look at a stepper motor and you go to actually apply the motor itself, one of the things you'll have to look for is something called side load on the motor. Because if you think about it, as soon as you begin to rotate something rotationally, if you try and use the motor without a coupler and actually have the load move back and forth, like attach a belt drive right to the motor and move mass back and forth, this motor shaft starts to see that every force, there's an equal and opposite force. The motor shaft becomes the equal and opposite thing that it has to, if you're going to push the mass, it has to push against something, and the something ends up being the motor bearings. And these are tiny little bearings, and they're really designed only to spin the motor. So the side load on hot dog style motors is fairly low. And by low, I mean maybe you can put on a motor like this. So if I had that motor, okay, first of all, you can kind of tell if I had this motor here, this is about a 3/8 inch shaft. And you can start to see where the bearing is. It might handle a little bit more load, but this motor, this motor here, this NEMA 17 motor, I'll bet you that you can't even find a side load specification for it. And when you go to look for a spec and you can't find the spec, how much can I load this motor on the side? And then there's also usually one for axial load, but that's most of the time that's much less of an issue, is the axial load. It's the side load because you're trying to push, you get torque out of the motor, and torque pushes something one way here and the other way on the bottom. Sometimes they don't even list it. And if you take these motors apart, a lot of times these NEMA 17 motors don't even have bearings. They're just bushings inside. They're only designed to rotate. They're not designed to, I see sometimes where you'll see a 3D printer and they'll have attached a pulley directly to the motor itself. And then they ask the 3D printer to go back and forth. and you look at the system and the motor's stationary, and the only thing that is, you know, if you're going to cause force, a mass to go that direction, something's going to push on the shaft that direction. And this doesn't even have a spec for how much you can side load it. You move up to a motor like this. This is a NEMA 34 motor. You guys have seen these before in 140. We use a lot of these. But all of a sudden, here is the bearing. You can see the big bearing in this. This actually, you can put a side load. The reason we actually use these in 140 instead of NEMA 23s all the time is because the students end up designing things that need a fair amount of torque, but they want to attach directly to the shaft. And rather than do a whole separate bearing structure and couplers to properly do the loading, we just bought some fixed couplers from Ruland. Actually, they donated them. And you could attach your stuff right to this shaft. And there's got a big enough bearing in here that you could get away with driving loads directly on the motor shaft. But it's definitely something you always have to look at when you're applying a motor, is what's the side load. The side load, just as a number for this, is probably only about 20 pounds, which isn't very much. When you start to add up the torque that you're able to get out of this motor and what diameter pulley, and it easily gets used up. A NEMA 23 is just a few pounds of side load is all you're allowed to really put on that. And so one of the advantages of the direct drive motor, in order to do something with this, you then have to find a separate bearing. You would do, you would do like a motor and the motor shaft, and then you do a coupler, and then you do something like a bearing and another bearing. And then in between there, you might put your pulley. So it's tempting to put the pulley right onto the motor, but that's F. And F then creates force against the motor shaft bearing. It has to push against something, right? So as soon as you go to the pulley, now when you have F, a force, let's say this is a belt kind of thing, and you're actually running a belt along here and moving a mass back and forth on a belt. This can move the belt, and these then take the force, and they're designed for that. This bearing in the motor here is really just designed to hold the motor in place. It's not a very useful bearing. So beware of that. So if you want to do something like move loads that are large inertia, you kind of have to do all this lineup, and there's a bunch of parts that you have to buy. Not to mention, you probably should have done some sort of gearing operation on this. You probably should have had motor plus gearing to get it right. As soon as you go over to the direct drive motor, even though this motor might be $2,000, which is in quantity one, of course, quantity 1,000 or quantity 100 for a robot manufacturer or somebody that's buying them and putting them into a machine or into a device that they're trying to sell. I think of robot manufacturers because the natural knuckle, or anytime you have a arm in a robot, the natural thing is you got to either do gearing and a motor to get the torque and speed in the right area, or you got to do direct drive. It's one of the only few places that you can get high volume, but this bearing can support loads. It can support loads, and they give you tapped holes around the outside, so you can bolt the load right to it. It's a high inertia, relatively, so when you get later into control issues, which I'll describe in motor sizing, you don't have problems with near as much. Okay, let me just clarify that. When we're dealing with a system like this one over here, we get to control the motor itself, but along the way, there is windup, there is deflection, there's a spring right there. A coupler is a spring. There's another shaft, and attachment point here. There's a belt. There's all sorts of springs in this system in order to make it really work. It's not a great way to do precision motion control. Over here, the load attaches directly to the motor, and there are 0 springs in between the motor and the load, 0. So when the load moves, it moves exactly the same as your motor. Your transfer function gets rid of all of these K terms. All those, I don't know if they're S's or S squareds, I can never remember, but all those S's in the Laplace, gone. It's the mass. And there's no spring. That's a huge deal in terms of you want to do something, these are high bandwidth systems. Meaning that's bandwidth. I talked about bandwidth way early on, but it's basically instead of bandwidth typically is frequency versus amplitude. But in a machine, right, and it's got some sort of drop off like that, and there's the part here that it drops off 3 dB, and here is then the bandwidth of the system, and I replace amplitude and frequency with accuracy and throughput. Because that's essentially when you mechanize something, what you get is you're either going to get more accuracy by slowing it down, or if you want more throughput and want to run it faster and faster, there's going to be a point in time where you lose accuracy. It's the same exact trade-off. And so when I say a high bandwidth motor, what I mean is that you're going to get the motion you want at higher and higher frequencies because you're not setting up all those intermediate oscillations and things, damping and friction and whatnot. So very high throughput system is the direct drive motor.